A rational function is a fraction function. I'm going to start in a place we've already been. If you think back to the first semester, we actually graphed 1 over x. It was on our note card of functions to know what they look like. And 1 over x looks like this. Okay. So that's this function here. 1 over x minus 1. Now, there aren't any parentheses, but would you agree that 1 is definitely with the x?
Yes.
So what does a minus 1 do if it's with the x? Moves it to the right. Very good. So this function is that function moved right. Now, I'm also going to move the y-axis over 1 so I can kind of give myself a guide on these, what are called asymptotes. We'll learn that word today. I was going to say, we already know it.
No, not
Oh, yeah,
4 years.
with exponentials. Okay, any questions about that one? Okay. What about the one that I'm going to make green? So right 1, which has already been done, and then up 3. I'm going to draw a horizontal asymptote there. I'm moving it up 3. Okay, any questions so far? I'm actually going to just do a new grid for the last one. Our other grid's kind of clouded up. So this is the normal graph. Then I am multiplying it by -2. Is that what I'm doing? 1 over x times -2. Wouldn't that good? 1, it'll flip it over the x-axis. And 2, it will vertically stretch it by 2. Or it'll multiply all the y values by -2. So instead of this y value being +1, it will be -2. Will look very similarly, just as a little stretch. Instead of this value being -1, it will be +2. You're right, the flip would make it 1 and then multiplying by 2.
You're right.
So the red graph is -2 over x. We're going to be looking at these functions a little more in depth. We're actually not going to be graphing yet today. You don't have to write this down, but a rational function is one where the numerator and denominator are polynomials. Yeah, x is in the numerator, x is in the denominator. We're going to be looking at 4 things today: vertical asymptotes, horizontal asymptotes, poles, and domain. Those are the 4 pieces of information we're going to pull out of rational functions today. We'll actually start graphing them tomorrow. Those of you who had me for Algebra 2, unlike Algebra 2, we will get to pick up the calculator, so we won't have to do it completely by hand. But we'll just have to use, what we're going to have to pick up is what the calculator can't handle. And the calculator doesn't handle asymptotes very well. So we're going to have to figure out where those are and what those look like and how to compensate for the calculator's errors. You are smarter than a calculator. Vertical asymptotes are straight lines with the equation x equals a number. So it's where the graph approaches but never touches. Horizontal asymptotes are straight lines with the equation y equals a number. Big thing you need to know, and I think you already know it. Horizontal asymptotes are y equals, vertical asymptotes are x equals. Something that's a common misconception is people always think that asymptotes can't be touched or crossed. And vertical asymptotes, that's true, but horizontal asymptotes can be both touched or crossed either way. They are just guidelines for what the graph does as x approaches infinity or negative infinity. The domain is a set of all x values. When we're finding the domain, we're going to ask, what can x not be? And for a rational function, the issue we have is a denominator.
Is to right now?
You don't have to. I think most of this is all information you already know.
I think we got enough for too.
You probably do for a domain.
So we haven't wrote notes since March 6th.
Maybe.
Sweet.
Vertical asymptotes and holes. These two things are commonly confused. Vertical asymptotes and holes both happen at undefined places on the graph, or when the denominator is 0. In fact, 3 of the things we're going to be finding today are going to be when the denominator equals 0. That's going to be a really big deal. If the denominator equals 0 and the factors cancel out, you get what's called a hole in the graph. If the denominator equals 0 and the factor does not cancel out, you get what's called an asymptote. Don't worry too much about explanation here. You'll see it when we graph it, when I show you a graph in just a minute. But that's the big difference in vertical and horizontal asymptotes. So if you have a factor in the denominator that cancels, you're going to get a hole from that. If you have a factor in the denominator that doesn't cancel, you're going to get a vertical asymptote from that. Again, this will make so much more sense when you example. So kind of the overall. This you need to write down. Up until this point, the writing you'll pick up in just a minute. But this you need to write down. If when we find a horizontal asymptote, we're going to be looking at a function with x's in the numerator and the denominator. Remember with polynomials, we learned that the leading exponent was the only thing that mattered for end behavior? So remember that? Same holds true for rational functions. As x gets really, really big, all of this stuff seems to not matter. And so the only thing that matters is the leading terms, the x over x cubed. As x gets really, really big, what does x over x cubed do? So think it would be like 1 over x squared. It would simplify. If numbers get really, really big on the bottom, what kind of numbers do you get when you get really big numbers on the bottom of a fraction? Small numbers, like 1 over a million. That's 1 million. That's tiny, right? 0, 0, 0, 0, 0, right? Tiny number. So if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is equal to 0. We're just going to follow these rules to find horizontal asymptotes. The degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is y equals 0. If that is flipped around, and the degree of the numerator is bigger, then there's no horizontal asymptote, because this function is going to approach infinity or negative infinity as x approaches infinity, because x cubed over x gives you a line. In fact, if you took pre-AP Algebra 2, you found slant asymptotes. We're not going to do that in here. We don't have to go to quite that depth in here, but we found slant asymptotes. That actually approaches a slanted line, not a horizontal line. So if the degree of the numerator is larger than the degree of the denominator, there's no horizontal asymptote. If the degrees of the numerator and denominator are the same, then the horizontal asymptote is the ratio of the leading coefficients. What does that mean? So, if you have the same coefficient, for same degrees on top and bottom. As x gets really, really big, nothing matters except the 3x squared and the 2x squared. What is 3x squared divided by 2x squared? What is 3x squared divided by 2x squared?
1.5.
Just 3 over 2? The x squared is canceled. So the horizontal asymptote would be the 3 over the 2. The ratio of the leading coefficients is just those two leading coefficients divided. We do need to make sure that our exponents are going in descending order when we're making these decisions, right? The highest power first. So these are the 3 rules we're going to follow for horizontal asymptotes. So today we're going to be finding 4 things: domain, vertical asymptotes, poles, and horizontal asymptotes. 4 things that we're going to pick out from a rational function. So let's look at this first example. We actually have 2 examples side by side. For the top 3 things, for domain, vertical asymptotes, and poles, on all 3 of those, I need to know when the denominator equals 0. So I need to factor the denominator and see when it equals 0. Step 1. Factor the denominator and see when it equals 0. So these happen to have the same denominator. How does that denominator factor? Very good. X plus 2 and x minus 3, same on both sides. So the first question I'm going to ask is, what is the domain? Remember, domain is everything x can be, but I'm going to ask, what can x not be? You tell me, what can x not be? Good. It can't be -2 and +3. Why? It's when the denominator equals 0. Why is that a problem? Try in your calculator. Try dividing 1 by 0 in your calculator. What's it say? Error. It can't do that. You can't do it. It can't do it.
1 divided by 0 equals.
Yes. Cannot do that. So we're going to write the domain 2 different ways. So I know that x can't be -2 or 3. There are 2 different ways to write this, and you need to know both. One of those is interval notation. You're very familiar with it because I've been making you do it all year. The reason I work with you so much on that is because it's the harder of the 2 ways to write it. So the interval notation for the domain is, can x be here?
Yes.
Yeah, so from -infinity to -2. Can it be between -2 and 3? Like 0? In fact, the only thing it can't be is -2 and 3. So that's the domain of interval notation. Because there are 2 things it can't be, it gives us 3 different intervals that it can be. It's broken up twice.
So shouldn't it be
Good question. If it can't be negative 2 and 3, why are they up here?
Because it's what's in between.
It's what's in between those values. And how did I indicate up here that I don't want to include 2 and negative 3? Parentheses, right? Parentheses say not including. Sorry. It's just a notation. If you leave it out, I'm not good.
Oh. The U is.
Okay, any questions about this notation? This is the more difficult way. I need you all to listen. This is the way I want answered on your homework. Because it's the harder way, it's the one you need more practice with. So I want you to answer it this way on your homework. However, on multiple choice tests, they also use set notation, so I want you to be familiar with what it looks like as well. I don't want you to answer with it because I think you could always pick it out.
What is the last thing?
This is not the time for that question.
Oh. Oh, it's
Okay, so this is this second option for notation. I think you could all pick it out in a multiple choice lineup because it just says x where x doesn't equal negative 2 or 3. It's the easier option. The interval notation is more difficult. Both of those could appear as multiple choice answers. The top one is the one that you would be tempted to mess up. For example, you might be tempted to leave out the negative 2 to 3 portion. So that's the part we're going to focus on today and practice today. Turns out this domain is completely identical to the other one because, why? Same denominator. The only thing that matters for domain is denominator.
What's the line between the two?
It means such that, and so if you read this in set notation, it's x such that x doesn't equal negative 2. X with a line there.
So which way do you prefer to write it?
I want to see interval notation on everything. This one. And in fact, this is the last one I'll probably do set notation on. Again, the reason I focus on interval notation is because it's the harder one to figure out on your own. Set notation, if you saw that in multiple choice, you'd go x not equal to or negative 3. Oh, I can do that.
Can we do either?
On the test, you'll need to know both. For multiple choice purposes, open response. I want to see interval notations. For me. The final, this will be multiple choice. Say that again.
What is the top interface that's called?
Has it? Yes. Okay, everyone listen. I have heard, y'all didn't even hear his question, and it was a good one. I need you to stop talking while I'm talking and while other people in the side conversations, and wake up. Both of those things will be good. Okay, so far with domain, nothing has mattered except the denominator. Tristan? Okay. Alright. Let's talk about vertical asymptotes. Vertical asymptotes are places where the domain is undefined. So either at 2, negative 2, or 3, right? When we identified this negative 2 and 3 up here, we also identified our possible vertical asymptotes and possible poles. So that negative 2 and 3 actually will help us with all 3 of those first questions. What we're going to do is we're going to look at the factors in the numerator and denominator and see if any of them cancel. In the first one, do any of them cancel?
No.
No. So, both of those numbers are vertical asymptotes. In fact, most of them are going to be vertical asymptotes. However, if you have something like this one, you see this x minus 3? It cancels. It is not a vertical asymptote. It's a whole. So, on vertical asymptotes, this one only has 1. It's just at negative 2. And then for holes,
It would be
3.
hole at 3. If you will, get your calculator out and graph this equation for me. X minus 3 divided by x squared minus x minus 6. Yeah.
Still don't understand the whole.
The holes.
No, the vertical asymptote.
Okay, so the vertical asymptotes, you see how we got this -2 and 3? And remember those were domain problems? That's either a hole or a vertical asymptote. One of the two. If it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote.
So it's like you have an x minus 1 and
On the bottom.
yeah.
Right. Okay, if you will, look at that graph. Right, and I'm going to show you that really quick. If you look at your calculator on this graph, I want to show you the difference between a vertical asymptote and a hole and how those work out in your calculator.
Can you just have a
You can. Most of the time, if you do, it would look like a line with a hole in it or something. Hey, put this in Y1, and in Y2, I want you to put 1 over x plus 2.
You always tell us it's zero.
In Y2, I want you to put 1 over x plus 2. When do you do that? Why? Finally equals 0. Yes. Your calculator can't quite handle an asymptote. Has an asymptote at -2. No, remember I said your calculator's going to have a hard time with asymptotes. So, but it's got a vertical asymptote at -2. 1 over x plus 2.
Yeah, mine's not.
Oh, it's doing the same thing. Here's the thing. Everyone look at this.
Because that's what you have to.
If I cancel the x minus 3s, wouldn't I be left with 1 over x plus 2? Could I graph 1 over x plus 2 that I did on the bell ringer? It's a rational extended left hand. Is that what your calculator looks like?
It seems to be like that.
So, what's the difference in this big messy equation and this simple one? The x minus 3. And what does that create? Well, if you will, go to your table and type in 3. In the Y1 equation, what do you notice when you type in 3?
Error.
But in Y2, you don't get an error. So at 3, there is a hole in this graph. You can't see it on your calculator because your calculator doesn't have enough pixels to make a hole. But it's there. Otherwise, those two graphs look completely identical. So that x minus 3 on top and bottom just made what's called a hole. It's just a little blip in the graph where there's no y value there. But everywhere else, it just looks like 1 over x plus 2. Because that's 1 over 1.
What is it?
There's just no value there. There's just a little pickup spot.
It stops.
Right.
I want this
We'll talk about that later. Today we're just trying to figure out how this graph works. But yeah, we will. You can keep zooming and eventually it may show it to you, but calculators really struggle with holes.
How do you know how to use
You don't have to know that. Today all we're doing is identifying holes and asymptotes. But the way I knew this when this canceled, that's what was left. Hey, no talking. I am having a very difficult time. I'm going to have to start writing detentions. I've never had to do that. I've got to get you quiet so I can finish the lesson, guys. Hey, so, recap. Domain, vertical asymptotes, holes, all very similar questions. When you identify the problems with the domain, those problems either are holes or vertical asymptotes. So once you've answered the first part, the second part is easier. You just have to figure out which one's which. Now let's talk about horizontal Okay. For horizontal asymptotes, I'm going to follow those rules. I'm going to look at the degree at the top. What is the degree at the top? And what's the degree at the bottom?
2.
So the bottom's bigger?
Yes.
So what's the horizontal asymptote?
0.
Y equals 0 on both of them.
So, oh, is that one of the rules?
As x approaches infinity, if you were to look at this graph, it levels off at y equals 0. And we just found that from that equation by following the rules. So we wrote down on the we just have to follow the rules. From the graph, the degree of the numerator is 1, degree of the denominator is 2, the denominator is bigger, and so that was rule number 8. Rule letter 8. Okay, let's look at the next one. Just to save us time, I factored it for you. You will have to factor it on your very own. But so I went ahead and factored this just to make it speed up a little bit. So I'm going to start with domain. What am I going to ask myself with domain? Yes, what is the domain? When does the denominator equal 0? Because that's a problem. Right? 3 and negative 3, agreed?
On both sides.
So to do interval notation, I'm going to draw a number line. Right, Matt? Yep. I'm going to put negative 3 and 3 both on the number line. Negative 3 and 3 both on the number line. I'm going to look at all of the other places on that number line. That's my domain. So I have 3 different intervals. Okay. If you have 1 domain error, you'll have 2 intervals. If you have 2 domain errors, you'll have 3 intervals, and so forth. So my domain is negative infinity to negative 3, negative 3 to 3, and 3 to infinity. The biggest error on this domain is leaving out the negative 3 to 3. And you better believe on a multiple choice test they're going to have that as an option. So be careful about that.
Wasn't there like a rule where like you try to figure it out and you get like the x, like it didn't match or something?
That's solving inequalities. But we do use interval
So
notation.
with all of these, it's just they're all going to kind of look like that.
Yeah, they'll be very similar.
So when we write the domain, we always write the in between.
Yes.
Like the whole thing, even if there's a hole.
Yes. Domain does not matter whether your holes are asymptotes or addition. So it doesn't matter if your holes are asymptotes, doesn't matter anything, it just matters what x can be. And x can be anything except 3 and negative 3. So it could be anything from negative infinity up to negative 3, it could be anything from negative 3 to 3, and it could be anything from 3 to infinity. It just can't be negative 3. Yeah, very similar. I mean, you'll have to pay attention to what makes the denominator 0. Put that on the number line, but then from there, it'll be very similar. Vertical asymptotes. Which one cancels? Yeah, it's minus 3. So, that's a hole. Well, what is a hole? X equals what? 3. 3. Why is 3 a hole? That's what makes it equal 0, right? That's the problem spot there. And so what's the vertical asymptote? Just the bottom. All 3 were only the bottom.
So we need to find the holes before we find our spots.
You do. Those are the ones that cancel, vertical asymptotes are the ones that don't. You kind of end up finding them together.
The only reason you look at the top is to find holes.
To find which ones switch vertical asymptotes versus holes. Hey! Clear the distractions. Whatever you are doing that is not writing notes and paying attention, stop. This table in particular. Focus. Okay. Any questions? I don't want to hear any talking other than what's going on here. Ask me or don't ask me. Normally I don't feel that way, but today y'all are just really struggling to get off spring break, I think. No. Holes are the ones that can't stop. Does that make sense? And the reason it's positive 3 is because positive 3 is what makes x minus 3 equal 0. So that's the reason the hole is positive 3. None of the things we're finding today have anything to do with the numerator, except for holes versus asymptotes. Right. So everything, holes, vertical asymptotes, and domain, all have to do with the denominator.
This is going to be that one, like, that's a horizontal asymptote, right? Because
yes. Good. So for horizontal asymptotes, the degree of the numerator and the degree of the denominator are the same, both x squared. This is a 1 and this is a 1. So 1 divided by 1 is... So my horizontal asymptote is y equals 1.
Ooh, you get one.
Okay. I will count it off if you don't put x equals or y equals on vertical asymptotes and horizontal asymptotes. The reason I'm picky about that is those are equations of lines. So I need to know that it's a horizontal line y equals, and I need to know it's a vertical line x equals. Okay? This one I put up here because it's kind of a trick question, sort of. It occasionally comes up. Maybe, I don't know if there's one in your homework or not. This occasionally happens. Does x squared plus 9 factor? Does x squared plus 9 equal 0? No.
Wait, so how come it doesn't factor?
It's not.
It's
minus
9.
Right. It's a sum of perfect squares, which is not something you've ever heard of because it doesn't exist. There's no factoring rule for that. It has to be a difference of perfect squares, right? It has to be subtraction in between. So it doesn't factor, and in fact, if you were to side note and say, well, when does x squared plus 9 equal 0, you would get, and do I show up on graphs? So the domain is all real numbers. There are no vertical asymptotes, there are no holes. If the denominator equals 0, it wipes all those out, right? Whatever this looks like, it doesn't have any breaks in it. It's a continuous function. So that's a little bit strange when the denominator doesn't equal 0. I just wanted you to see what that looks like. Talking about horizontal asymptotes.
None.
Why none? Good. The top is bigger than the bottom, and that rule is that there are no horizontal asymptotes.
So does this graph even make sense?
Oh, it does. It's actually prettier than some of the others. It's continuous. There are no breaks in it. Vertical lines. No asymptotes. No. Okay, let's do one more. I want you to try this one by yourself, and I'll pass out papers. This is the last example. No, the last one was only tricky. No. I think this is unit 7, but I think it's actually the second half of chapter 6. No, do it. Yes, as a grade, remember, always grade is contact. Yes, it does.
Oh, really? Okay.
domain. Factoring the numerator would be a waste of your time for domain purposes only. So for domain, what is domain?
Negative infinity.
Okay, any questions about that one? No, those are a U, they're a union symbol, and they stand for combining two sets together, so don't make all three. Very rarely will a math teacher ever count off for not putting them, but you'll see them on the test and stuff. Vertical asymptotes. So figure that out. What do I need to do? Back to the top. Greatest common factor of 2 factors out. You could probably even stop at this point. I'm going to go ahead and finish factoring it, but are there any common factors on the top and bottom? So what does that mean for both 2 and negative 2?
No.
It is very typical to get no holes. Remember, to get a hole, you have to have that very special case where you have a factor on top and bottom that are the same. So unless a math teacher's making a problem up, it's a rarity in the real world.
But again, happens if your bottom does not factor.
If the bottom doesn't factor, then to solve it equals to 0 if it's quadratic, you'd have to use the quadratic formula or the calculator to find the exit or the steps of that denominator. You would find it using, you would set the bottom equal to 0 using the calculator. Horizontal asymptote. Why is it 2? Lucas? I'm having a hard time to do that. Okay, your table. Either way.
I thought it was the factor.
I don't want to know why. I want you to stop. Okay, so the degree of the numerator and denominator are both 2, so they're the same. And then we look at the 2 leading coefficients, 2 and 1, and 2 divided by 1. How do we feel about these 4 things? Domain, vertical asymptote,